Okay. I guess I'll get started. So, your homework on chapter 5 is due on Wednesday. Your homework on chapter 6 will be due the week after, on the 8th. So this week we're going to finish up chapter 6 and start chapter 7. And next week, on Monday, we'll have a review of chapters 1 through 6. And then on Wednesday, we'll have the test on chapters 1 through 6. So I'll review before the test. That's next week. So next Wednesday is the test. About 10.
Are they
Yeah.
all choice or not?
No, they're problems you have to work out with partial credit. Some of them are multi-part, but about 10. They're about 10 points each. Yeah.
Oh, so the 100 points?
It's a 100-point exam, yeah.
Is it curved at all? No.
I curve the whole class. It's easier to curve at the end.
All right.
Name? It's just, so, I mean, you get partial credit, so there's some level of curving inherent in that process. So show your work. So I'll give you partial credit for showing your work, that kind of thing. So, chapter 5 is due on the 1st, chapter 6 is due on the 8th. There's a review of chapters 1, you'll have a review of chapters 1 through 6 on the 6th, and the chats on chapters 1 through 6 will be on the 8th. You won't need a calculator, you'll get a sheet of notes. You get one sheet of notes to use as a formula sheet. You can put whatever you want on it. And you know, yeah. And we will not have a lab that Wednesday because making you do a lab after giving you a test seems cruel. So I won't. So, when we last left off, we were talking about Hooke's law for springs and strings. Allie, right? I'm gonna have just someone else.
Passenger side door opening and suddenly he's we think
Okay, so we were talking about strings and springs. We have Hooke's law. Hooke's law is for springs. The force from a spring, the amount of force is Kx. This is usually written as force equals minus Kx, because the force is in the opposite direction. The force provided by the spring is opposite the direction that the spring is pushed or pulled. And that constant K is called the spring constant. So here we have a device for improving airflow through nasal passages. This is a nasal strip, which is 2 flat polyester springs enclosed by adhesive tape covering. Nasal strip exerts an outward force of 0.22 newtons on the nose, causing it to expand by 0.36 millimeters. Treating the nose as an ideal spring, find the force constant in newtons per meter. and how much force would be required to expand the nose by 4.1 millimeters. So we did this last time, so I'll just quickly go through it again. So the force is 0.22 newtons. The distance is 3.6 millimeters. We're trying to find the spring constant K in part A, and in part B, we want to find the force. If X is 4.1 millimeters, what is the force? So, part A, we want to find the spring constant. Well, ignoring the sign, because we're just interested in the magnitude, spring constant's always going to be positive, by the way. Force equals Kx. So K is going to be force over X. So 0.22 newtons over 3.6 times 10 to the minus 3 meters. K is going to be 61 newtons per meter. And the force required to expand by 4.1 millimeters, force equals Kx. So we have 61 newtons per meter times 4.1 times 10 to the minus 3 meters. Name? Your name? Which will give you a required force of 0.25 newtons. Any questions about Hooke's law? Springs? We've done a bunch of that in the labs, so you have some experience. Give people a chance to write this down. And yeah, we did do this last time. I think so when I looked at the video. But that's the general idea. For a spring, the force from a spring is minus Kx. So, next we have translational equilibrium. When an object is in translational equilibrium, the net force on it is 0. This occurs when an object is either not moving. Usually we're going to be talking about it not moving. If it's not moving, it's in what's called static equilibrium. But translational equilibrium is a slightly larger, more general thing. That is also includes if you're moving at a constant speed or velocity in a straight line. If you're moving at a constant velocity in a straight line, then your acceleration is 0, so your net force is 0. Almost every translational equilibrium problem is a static equilibrium problem, just because nobody wants, it's just easier to put together a problem that's not moving than one that's moving with constant speed. But the general idea is that the sum of all the forces equals 0. So, for example, if I have the physics textbook here, the sum of all the forces on this physics textbook equals 0 because it is not moving. So if I know some of the forces, I can use that to figure out the other forces and find out all the forces on the textbook. That's the general idea. And this can be expanded quite a bit. There's in fact an entire, if you want to go into this general idea, well, we'll go into more detail in a later chapter. But this general idea of all the forces add up to 0, and you also include all the possible rotations add up to 0. There's an engineering course on that called statics, which is not, we're going to cover pretty much all the basic fundamentals of that course in this course, but they just deal with ugly problems. So this is the calculation of unknown forces. So the general idea of translational equilibrium, all the forces add up to zero. Static equilibrium has got an extra factor. We'll get into that in a later chapter. But that involves rotation, and we haven't talked about rotation yet. So, but the general idea, if something is not moving, all the forces on it add up to zero. So here, for example, you have a bucket in a well that is not moving or moving with constant velocity. All the forces in it add up to zero. So if we look at the bucket, the weight pulling down plus the tension pulling up has to add up to zero. So the weight pulling down is going to be equal in size to the tension pulling up. If we look at the pulley, we have tension 1 pulling down on both sides and tension 2 pulling up. So tension 2 minus 2 times tension 1 will equal 0. So tension 2 is going to be twice tension 1. So here, for example, we have a person hoists the bucket from a well and holds the rope, keeping the bucket at rest, as in situation 1 here. Next, the person ties the rope to the bucket handle, so the rope holds the bucket in place, as you see here. In this second case, is the tension in the rope greater than, less than, or equal to the tension in the first case? So, in the first case, holding the rope, guy's holding the rope in one hand, the rope is holding up the bucket. In the second case, he's tied the bucket to both ends of the rope. So both ends of the rope are pulling up on the bucket. So is the tension in the second case greater than, less than, or equal to the tension in the first case? Anybody have any thoughts? Who thinks the tension here will be greater than the tension here? Not seeing any hands. Who thinks the tension here in this rope will be the same as the tension here in this rope? Think it'll be the same? Okay. Who thinks the tension here will be less than the tension here? I see some less. So this is sort of how you can work it out. Here, the bucket is held up by one rope. So that one rope has to provide a tension equal to the mass of the bucket. Balance it out. So the sum of all the forces is equal to 0. In case 1, tension minus mg, because tension is pulling up, mg is pulling down, equals 0. In case 2, we have 2 ropes pulling up. So 2 times tension minus mg equals 0. So in the first case, this tension equals mg. In the second case, 2 times the tension equals mg. So the tension is half of mg, mg over 2. So in this case, with 2 ropes, each rope only has to lift up half the bucket. So the tension is half of 1 rope. So it is less. Therefore, tension in 2 is less than tension in 1. So here we have a pot of flowers. To hang a 6.2 kilogram pot of flowers, a gardener uses 2 wires, one which is attached horizontally to the wall, and the other which is attached at an angle of 40 degrees from the horizontal to the ceiling. And we want to find the tension in each wire. So we know that T1 here is horizontal. We know that T2 is at 40 degrees above the horizontal. So we can break T2 into its component, its horizontal and vertical components. The other thing you can do is you can break those forces that have to add up to 0 into horizontal and vertical. And all the forces vertically have to add up to 0. All the forces horizontally have to add up to 0. Oh. I'll give you a few nice stories. So here, well, the one thing we know is the weight. So we'll start vertically. We know the mass is 6.2 kilograms. We know G is 9.81 meters per second squared. We know this angle theta is 40 degrees. We're trying to find T1 and T2. I guess I forgot to put those question mark values. We know the sum of all the forces equals 0. That means the sum of all the forces in each direction equals 0. So we'll start vertically because we know what the weight is. So the sum of all the forces in the y direction equals 0. So tension 1y plus tension 2y plus weight y equals 0. Tension 1y. Made a mistake. Let me check this right up. I got tension 1 and tension 2 switch. Yeah, these are, oops, this should be 0 plus. This should be tension 2, tension 2, We'll just work this one out. So I'd gotten the 1 and 2 switched. So tension 1y plus tension 2y plus weight y equals 0. So tension 2, 0 plus tension 2 times sine theta equals minus, tension 2 sine theta minus mg equals 0. So tension 2 sine theta equals mg. And I'll re-up the slides because apparently I got those T1 and T2 switched from what they are in the picture. I think it was just going from left to right. So T2 is going to be mg over sine theta. So 6.2 kilograms times 9.81 meters per second squared over the sine of 40 degrees, which is 94.6 newtons. And then we can look at the x direction. The sum in the x direction is 0. So T1x plus T2x plus Wx equals 0. So T1 minus T2 cosine theta equals 0 because the weight in the x direction is 0. I just left that out. So T1 equals T2 cosine theta. So 94.6 newtons times the cosine of 40 degrees, which is 72.5 newtons. Sorry about getting T1 and T2 mixed up, and I will re-upload these slides. Any questions? General idea, just make sure all the forces add up to 0. Here we have a 1.85 kilogram bag of clothespins that's hanging on the middle of a clothesline, causing it to sag at an angle theta of 3.5 degrees. We want to find the tension T in the clothesline. Okay. So this is a similar problem. We have two tensions, they're at angles, they're both at 3.5 degrees above the horizontal, and we want to find the tension in the clothesline. So they're going to be applying tension times cosine theta horizontally and tension times sine theta vertically in this case. The mass is 6.2 kilograms. G is 9.81 meters per second squared. That is not the right. It's 1.84 kilograms. Ah. Why did I get 6.2 from? And this is 1.84, and now I need to check that the answer is right. Gee. Nope. I did it with 6.2 for some reason, and I have no idea where that came from. Yes. Yeah. But that's not the right number either. Jeez. So these will be re-uploaded with the working out fixed. All the math was correct on this. It was just I had the wrong mass and carried it through. 1.84 kilograms. G is 9.81 meters per second squared. Theta is 3.5 degrees. So the sum of all the forces is 0. If we look at the x direction, the two tensions cancel each other out horizontally. We get tension cosine theta to the left and tension cosine theta to the right. They cancel out. So we're interested in the y direction. The forces in the y direction are tension y plus tension y times weight y equals 0. That's T sine theta plus T sine theta minus mg equals 0. So 2t times sine theta equals mg. So t equals mg over 2 sine theta. So 1.84 kilograms times 9.81 meters per second squared over 2 times the sine of 3.5 degrees comes out to 148 newtons. Sorry about the mistakes on these. I will re-upload these after class. Luckily, there weren't any like mistakes in the reasoning. They were just oversights. Any questions? Nope. Okay. So let's talk about connected objects. So when forces are exerted on connected objects, their accelerations are the same. This means we can write basically systems of equations. We can use force equals mass times acceleration for each object and write systems of equations to find, say, total acceleration, the acceleration, the tensions, things like that. So if we have two objects connected by a string and we know the force and the masses, we can find the acceleration and the tension. So here you can see for object 1, for box 1, it's got the applied force F minus the tension equals mass 1 times acceleration, and the tension equals mass 2 times acceleration. If we treat each box as a separate system, this lets us find out what's going on. So if we want to find the acceleration, we can add these two. We'll see tension cancels out, and we'll get mass 1 plus mass 2 times acceleration equals force. The other way you can approach this is you can use a system approach. We can treat both boxes as a single system and say the sum of all the external forces equals the sum of all the masses times the acceleration of the system. So the external force equals mass 1 plus mass 2 quantity times the acceleration. And that's the same thing you get if you add these two equations together. Because if you add these two equations together, you get force minus tension plus tension. So, plus 0t equals mass 1 times acceleration plus mass 2 times acceleration. Tension cancels out. And you can find acceleration. If you want to find tension, you can substitute in, you can, for that, I would divide you can divide both by the mass and then subtract them, or there's a few ways you can. Or you can find the acceleration first and just plug it in one of the equations to find tension. Then sometimes you have a pulley that redirects force around tension around a curve or around a corner. The easiest way to deal with this is to just have the coordinate system follow the row. So you say, okay, for mass 1, x is across the table. But for mass 2 here, x is down. So acceleration is the same in both of these. And then we can easily write a system of equations. For mass 1, we have tension equals mass 1 times acceleration. For mass 2, we have weight 2 minus tension equals mass 2 times acceleration. We just let the coordinate system follow the string. Does that make sense? Or you can treat it as one big system where you have mass 1 plus mass 2, and the force applied is weight 2. So here we have two masses, mass 1 and mass 2. They're connected by a string that passes over a pulley. Mass 1 slides without friction on a horizontal tabletop, and mass 2 falls vertically downwards. Both masses will move with constant acceleration of magnitude A. Is the tension in the string greater than, less than, or equal to the weight of mass 2 g? And unfortunately, this picture is forked, but that's the one provided by the publisher. So, I can't fix it easily. So, do you think the tension in this string is greater than, less than, or equal to the weight of block 2? So who thinks the tension in the string is going to be greater than the weight of block 2? Nobody. Who thinks it will be less than the weight of block 2? Who thinks it will be equal to the weight of block 2? Well, all of you who said less are correct. Basically, here are the positive directions for acceleration. The sum of all the forces equals mass times acceleration. So the sum of all the forces on mass 2 equals mass times acceleration. M2g minus tension equals mass 2 times acceleration. This is a positive number, so tension is going to be less than M2g. Tension equals M2g minus M2a. So tension is going to be greater than M2g. I mean, less than M2g, because we've subtracted the acceleration. Sorry. No. If the acceleration was 0, they would be equal, but the bigger the acceleration, the less the tension is in the string. Now here we have that same setup. Block of mass 1 slides on a frictionless tabletop. It's connected by a string that passes over pulleys and suspends the mass M2. We want to find the acceleration of these masses and the tension in the string. And this is all symbolic. So we can set up systems of equation. So if we sum of all our forces equals mass times acceleration. So for mass 1, tension equals mass 1 times acceleration. And for mass 2, mass 2g minus tension equals mass 2 times acceleration. Because our axis is following the string. So if we add both equations together, tension will cancel out. We'll get mass 2g equals mass 1 times acceleration plus mass 2 times acceleration. We can combine like terms. We get mass 2g equals mass 1 plus mass 2 times acceleration. And we can divide both sides by mass 1 plus mass 2. And we get acceleration equals mass 2g over mass 1 plus mass 2. So that's our acceleration. Our tension is going to be mass 1 times acceleration. So we can just plug in tension will be mass 1 times mass 2g over mass 1 plus mass 2, or just mass 1 times mass 2 times g over mass 1 plus mass 2. That's, again, all symbolic. And if you wanted to, you can plug in some masses for mass 1 and mass 2 and find the acceleration. Here we have another one. This is called Atwood's machine. Atwood's machine consists of two masses that are connected by a string that passes over a pulley, as shown in this sketch. And we want to find the acceleration of the masses for a general mass 1 and mass 2, and then evaluate for the specific case of 4.5 kilograms for mass 1 and 5.5 kilograms for mass 2. So here, no, over here, mass 1 up is positive, mass 2 down is positive. And then you can work out, the forces for each. I'll give you a few minutes to work on it. Again, the basic principle here is going to be the sum of all the forces adds up to 0. Well, actually equals mass times acceleration, not adds up to 0. Sorry, moment of mixing things up in my head. So, if we work out sum of all the forces equals mass times acceleration. So for mass 1, tension is pulling up in the positive direction, M1G is pulling down in the negative direction. So tension minus M1G equals M1 acceleration. For mass 2, weight is pulling down, tension is pulling up, but down is positive for mass 2. So mass 2G minus tension equals mass 2 times acceleration. If we add these equations together, we get M2G minus M1G equals M1A plus M2A. Which is basically what you would get from treating it as a system. And mass 2 minus mass 1 times G equals mass 1 plus mass 2 times acceleration. So acceleration ends up equaling mass 2 minus mass 1 over mass 1 plus mass 2 times G. And that is with mass 1 up being positive and mass 2 down being positive. So if we plug in the numbers given, mass 1 is 4.5 kilograms and mass 2 is 5.5 kilograms. G is 9.81 meters per second squared. We have 5.5 kilograms minus 4.5 kilograms over 4.5 kilograms plus 5.5 kilograms, all times 9.81 meters per second squared. We have 1 kilogram over 10 kilograms times 9.81 meters per second squared, the difference over the sum, which comes out to 0.98 meters per second squared. Any question? So that's Atwood's machine. So the last bit in chapter 6 is circular motion. Let me find the thing I can use to demonstrate circular motion that will not seriously injure me. I will not be swinging the 1 kilogram weight around. Because I have managed to hit myself in the head with the weight I was swinging around in the past. So I definitely don't want to do that with a very large weight. So we have circular motion. So if an object is moving in a circle, it has an acceleration because its velocity is changing direction. If that is the case, this mass has an acceleration, so there must be a force. And that force is coming from the tension of the string. So if an object moving in a circle must have a force acting on it, otherwise it would move in a straight line, and the direction of the force is towards the center of the circle. And if you want to work out the formula for first principles, you can. If you have something with constant velocity traveling in a circle, you can work out its acceleration by taking the derivative. If you want, I can write that out, but I'm not, it's not something you need to know how to do for this class. So if you do a little algebra, you can get the magnitude of the acceleration and the force required to give an object of mass m moving in a circle of radius r. And the magnitude of this force is given by the centripetal force, which is mass times the centripetal force, which is mass times speed squared over radius. So basically, if you have something traveling around in a circle, speed x ends up being equal to velocity times cosine of I'm not going to work that out right now. I guess it's omega. Well, you could work it out, but with if you want, I'll write it out. I'll work out how you get this formula just from calculus, but this is the formula: velocity squared over. This force can be provided by the tension in a string. Say the normal force if you have a banked curve, or if you're on a roller coaster going around a loop, that's being provided by the normal force, or friction, among others. So when you drive around a curve in your car, that's friction providing the centripetal force. So, force centripetal is mass times velocity squared over radius. So you can have the normal force providing it, which is what's happening in these cases. Here it's from a string, here it's from friction. And if an object is also changing its speed as it moves in a circle, in that case, there is also a tangential acceleration. We'll get into that more when we get to actually talking about rotation and other circular stuff. So if you have a 1,200 kilogram car that rounds a corner of radius 45 meters, the coefficient of static friction between the tire and the road is mu static, which is 0.82. What is the greatest speed the car can have in the corridor without skidding? So 1,200 kilogram car rounds a corner of radius 45 meters. Coefficient of static friction between the tires and the road is 0.82. What's the greatest speed the car can have in the corner without skidding? So we know the mass of the car, 1,200 kilograms. We know the radius, 45 meters. We know mu static is 0.82. We know G is 9.81 meters per second squared. We're trying to find the maximum velocity. To know that, we need to know the maximum static friction and the normal force. And the centripetal force. All the forces in the y direction add up to 0. That's the normal force minus mg equals 0. So the normal force equals mg. The centripetal force equals the force of static friction. And that's mv squared over r. So mv max squared over r equals force static max. And force static max is mu static times the normal force. That equals mv squared max over r. So v squared max is mu static times the normal force times the radius over the mass. My animation order is screwed up, I think. V max is mu static ends up being the square root of mu static times g times r. Because v squared max is mu static mass mg r over m. Mass cancels. So v squared max is mu static times g r. Sorry about the animation order screw up. I'll fix that as well. V max thus is equal to the square root of 0.82 times 9.81 meters per second squared times 45 meters, which comes out to 19 meters per second. Quickly fix. Why are we not? Move this down a little, and then click animations. That worked. Everybody got this? Okay. So if a roadway is banked at the a proper angle, a car can round a corner without any assistance from friction between the tires and the road. We want to find the appropriate banking angle for a 900 kilogram car traveling at 20.5 meters per second in a turn of radius 85 meters. So here, the weight, you can figure out the normal force is going to end up being the weight times the cosine of the angle here. And then that component of the normal force times sine of the angle will give you the inwards force that provides the centripetal force. So for this, our centripetal force is coming from the horizontal component of the normal force. We know the mass is 900 kilograms. We know the radius is 85 meters. We know the velocity is 20.5 meters per second. G is 9.81 meters per second squared. We don't know what the angle is. We need to know what the normal force and the centripetal force are. So vertically, the sum of all the forces equals 0. Horizontally, the sum of all the forces in the x direction equals the centripetal force, which equals mass times velocity squared over the radius. So if we look at the vertical component, that's normal force times the cosine of theta minus weight equals 0. So normal force times the cosine of theta minus mg equals 0. So the normal force times the cosine of theta equals mg. So mg over cosine theta equals the normal force. Because the forces vertically equal 0. But the forces perpendicular to the surface don't equal 0. That's the case. That's why this is different from sliding down a slope. Now, if we look at the x component, the x component of the forces, the only force is the horizontal component of the normal force. That's n times sine theta. That equals mass times velocity squared over radius. Normal force is mg over cosine theta equals mass times velocity squared over radius. If we divide both sides by mg, we get sine theta over cosine theta equals velocity squared over g times radius. Mass cancels. So we get tangent of theta is speed squared over g times radius. Well, we know the speed, we know g, we know the radius. So theta is just going to be the inverse tangent of speed squared over g times radius. So the inverse tangent of 20.5 meters per second quantity squared over 9.81 meters per second squared times 85 meters, which is 26.7 degrees. And I guess we have time for one more problem. So while driving along a country lane with a constant speed of 17 meters per second, you encounter a dip in the road. The dip can be approximated as a circular arc with a radius of 65.1 meters. And at the bottom of the dip is the magnitude of the normal force exerted by a car seat on a passenger in the car greater than, less than, or equal to the passenger's weight. And what would that be for an 80 kilogram passenger when the car is at the bottom of the dip? Okay. So mass is 80. So for part A, you're gonna have more normal force than you would than your passenger's weight, because you're also because you're accelerating upwards. Mass is 80 kilograms, radius is 65.1 meters, velocity is 17 meters per second, g is 9.81 meters per second squared. We want to find the normal force. Now, for that, we need to know what the centripetal force is. Forces in the y direction equals the centripetal force, which is mass times speed squared, or velocity squared over radius. That is the normal force minus the weight. So the normal force equals the weight plus mv squared over r. Thus, normal force is greater than weight. So normal force plus mg equals mg plus mv squared over r. So mass times g plus v squared over r. So 80 kilograms times 9.81 meters per second squared plus 17 meters per second quantity squared over 65.1 meters. Gives you 80 kilograms times 14.24 meters per second squared, or 1140 newtons. And that is where we're going to stop for today. We are basically done with chapter 6. We have like one more problem, and which we'll go over, and some review. And we'll be able to start chapter 7, and then we'll do the review next week. Monday will be review, and Wednesday will be the exam.
I even looked like a review presentation thing on,
It should already be up there.
oh,
And it should already have the problems worked out. Let me just check that that is the case. But save. Let me, I'll stop sharing and